I hope you can see my screen. And
Yes,
today,
it's visible,
I
sir.
yes, today there wouldn't be any problem regarding the internet because I'm in the lab, I guess so. Anyway, let us start. Welcome to the week two live session of discussion sessions of molecular spectroscopy or physical chemist perspective. So today, our agenda would be to discuss a little about the rotational spectroscopy basics, and then we will solve some numerical problems on it, as Professor Datta has taught you in the uh, second week of the lecture series, right? So again, we can see the electromagnetic spectrum, and our interest of today is this microwave region. So this is microwave spectroscopy. This is the region we are interested for today's discussion. Now, let us gather some information, maybe some useful um, formula, I should say, or let me write rotational spectroscopy. So here we are not going to derive the Schrodinger equation which is required. Actually, as I told you that the quantum mechanics is a or quantum chemistry is a prerequisite for this course. So we will means in principle we will think that that has been already you already have the knowledge prior knowledge of quantum chemistry, and then we are building our knowledge on this molecular spectroscopy, and the first thing we are encountering uh, process is the rotational spectroscopy. Now, for rotational spectroscopy, what are the to start with, suppose what is the selection rule, or what is the selection rule? So we will not. So in the lecture series, actually, Professor Datta has already taught the conditions. Means he has derived the selection rule. To be honest, so selection rule cannot be derived. Means he just showed that for which conditions the rotational or the microwave activity will be there in a certain kind of molecule. So that has been shown in the class. So first of all, for any transition to happen, the transition moment integral, or in short TMI, should be non-zero, right? And that is suppose minus infinity to plus infinity. Your state of final state, your dipole moment. Let me write mu zero, and your initial state d tau is the volume element should be non-zero for a transition to be allowed transition. So for uh, so this is the rule for all kind of spectroscopy, rotational, electronic, vibrational, or now for specifically for microwave spectroscopy, what have been done is, or what have been, let me start with the, uh, maybe before this we can start uh, discussing maybe the system we are interested in, right? So, uh, first of all, your selection rule or conditions, selection rule for microwave activity. Shomitra, can you give me the answer? What could be the major condition? So before going to the selection rule, there are some major uh,
Dipole moment, sir.
dipole
The
moments.
molecule
So
must contain have some dipole moment.
yes, so the molecule must have dipole moment, or the molecule should be polar. So oxygen, chlorine, then nitrogen, this kind of molecule is not microwave active. So generally HCN, then CHCl3 chloroform, this kind of carbon monoxide, these are microwave active, right? For these molecule, we can get a microwave spectra or rotational spectra. So this is the first condition. So this is the, we should say this is the star condition, star. Now what else? Now after that, this is the main condition, and then another one should be your delta J, where J is your rotational quantum number, right? That should be equals to plus minus 1, right? And also we have understood that delta M, during the transition there would be, when there is a change in uh, delta J, there could be some change in delta M, the associated uh, magnetic quantum numbers also, right? So for like for a hydrogen atom, so there delta M can be 0 for the Z active microwave activity, and for XY direction you have understood that delta M can be plus minus 1, something like that, that has been taught, right? Now
Sir, I
uh,
have a question.
yes.
How do you discriminate between that is the polarization is along XY axis or along Z axis? It is
So
like
you
uniform.
you need to, so for that also, suppose now for your dipole moment, see, so your dipole moment we are writing mu 0, but that is actually a sum of your mu 0 x, I should say, on x direction, mu 0 y, and mu 0 z, right? So this is something like a, you should say these are vectors, right? So mu 0 x, what is that? That has also been taught, right? Your, oh, sorry for that. Okay, let me come back. Uh, mu 0, something like sine theta cos phi. Now your mu 0 on y direction is mu 0 sine theta sine phi, and this is your mu 0 cos theta. Now you, sorry, this should be theta, not phi. Now you, what you do is you take a triple product of your initial state, your dipole moment, on whichever direction you want to see if it is polarized on that direction or not, and then the state or the wave function of your initial state, and you take a, you do the, either this, either you can do a triple product using your symmetry rule or something like that. So you need to get a non-zero dipole moment along that particular direction. Suppose you are working with mu 0 z. Now if your triple product along mu 0 z coming to be no, your non-zero, the transition moment integral, then you, it is allowed along z direction. If it is allowed along x direction, then the TMI along x direction would be non-zero, like that. Are you answered?
Okay, sir. Actually, my doubt is about, let's say I have applied some electric field or magnetic fields. Let's say I
Hmm,
applied an
hmm,
electric field in,
hmm,
let's say, certain direction is there.
hmm,
In that direction, I applied electric field, and my light is basically all that way there is electric field and magnetic field is associated with that, and it has all sorts of direction is there.
hmm.
Okay. So which will get activated or which will not get activated? I just want to know
It
that.
be for that you see this. So when you measure this non-zero transition moment integral, you don't really do it in a means I will not say in explicit integral. So what you see is that if the integrand is the triple product of the integrand, or the that integrand is symmetric or asymmetric, depending on that your total integral is going to be zero or non-zero. So you take the symmetric property of that. Suppose you are applying some electric field, and then you see so it will change your dipole moment operator, right? So your so this then this operator is going to be changed, some perturbation will come. So then you do that symmetrical integration with then your triple product change. Then your it is not only mu zero, then there is some perturbation associated with this operator also when you put an external electric field or magnetic field. And depending on that, you have to see that early your triple product is zero or non-zero. So
Okay,
means
okay.
when you
Yes.
apply a external field, your operator or that is going to change. Some additional term is going to be added on that. Like that, we are going to discuss uh, during the vibrational spectroscopy. Maybe I have to see when
Okay,
to be. Let me not give you spoiler. Okay,
okay,
let's see that if we are going to discuss something like that. I also forget. I have to also have to see. But for that, when you apply something, for that also you have to do a triple product, and your external field is there on the your updated or perturbed operator or even on the wave function. Okay. Now your delta J should also be plus minus one. I'm not going into the details. There are some recursion relations was also discussed by Professor Datta, right? And that was required when you were doing the integration for the conditions for the microwave activity. There you saw that how your delta M is zero for the Z direction, and delta M have to be non-zero or to be specific plus minus one for your microwave activity. And the main condition, foremost condition here, that it should have some dipole moment. Then comes delta M, and then comes delta J. So there are almost three selection rule or conditions, we should say, and that was coming from the recursion relations with the help of recursion relations and all. Basically, you treat your so in rotational spectroscopy, the easiest system we think of is that diatomic molecule. Suppose that is as we told, HCN or HCl, hydrochloric acid. So there are H and chlorine atoms are there. Now, it is like a two-body problem. But from two-body problem, discussing two-body problem is will be a little difficult. So what we try to do from a two-body problem, we try to form a one-body problem using center of mass and other a center of mass problem, treating it as a center of mass problem, we make it a one body problem. And there, the rotation of gyration becomes our rotational, that radius of radius of that mass, and that mass become reduced mass, right? So here comes, so here, that's why I am writing your mu zero as your dipole moment. So reduced mass, concept of reduced mass and other things come, right? Reduced mass, that is mu, is your two atoms, suppose Ma and Mb, divided by Ma plus Mb. And then, sorry, I should, okay. So, and your radius of gyration is something like the distance between the radius between the two van der Waals distance between these two atoms. Anyway, so now other concept which was important to us so I am writing these things so that we formula so that we can go to directly to the numerical problems. So what is the energy we can get? So when your this operator is working on your spherical harmonics, right? Depending on theta and phi, what are you going to get? It is actually something like your total angular momentum operator divided by 2I, where I is your moment of inertia operating on your spherical harmonics, and that when L square of the total angular momentum, that when it operates on the spherical harmonics, that gives us L. So for the rotational spectroscopy, we are going to write it as J, right? J into J plus 1 H cut square, right? And obviously divided by 2I. Now this is in uh, so this actually in the SI units, right? Now suppose so this is your energy expression. In quantum mechanics you don't write it like that. You take a means what you do for the energy, what you need to do, you need to have the, so let me write it maybe here on a different color. So your, when you measure the value, it would be something like your psi psi f, let me write it like that. Your two psi, maybe psi only. Let us not go to the difference. Psi, then your operator E, okay? So that is going to give you the psi, and you don't know if your psi and psi is normalized or not. For that, you use this. So that is known as the measurement theorem, right? How you measure it. So better I should not write it like this. So it would it would mean something else. Uh, are you getting my point? What I'm trying to say? Actually,
Yes,
your EJ operator is directly given by suppose L square by 2I. Now, if you want your EJ to be so, and your spherical harmonics is, we are thinking like it is already normalized. So, so eventually that will be your integral of y star theta phi multiplied by y theta phi in d theta and d phi, and that would lead to 1. And oh, I have missed this. Anyway, so your energy is given by this J into J plus 1 H cut square 2I. Now, in most of the cases, we are going to deal it within the centimeter inverse scale. That is also known by this terminology. Energy in, so this is in SI, and so you get it in EJ. That is nothing but your EJ. That is in joules divided by your Planck constant multiplied by your speed of light in vacuum. So that is J into J plus 1 H divided by 8 pi square C I. And this term 8 pi square Ci is known as a rotational constant, right? And this is not actually a universal constant. This is constant for a specific molecule or specific for a specific molecule. So this is known as your B. That is your H 8 pi square Ci, and how it is related to your energy EJ, that your now EJ becomes B into J into J plus 1. And you will see when you calculate the values, I am not writing centimeter inverse right now, but you will see when you put the values, you are going to get your answer in centimeter inverse in like in wave numbers. Okay. Now, what else we want to know from the rotational spectroscopy, that what is the so suppose then what is the value of the uh, lowest, what could be the values of J? Can you tell me? The J is your rotational constant.
J may be 0 plus minus 1, like that.
Yes, rotational quantum number, not constant. Constant is your, it could start from 0 and go to 1, 2, 3, like that. Okay, it could start from 0. So, first of all, your J equals to 0 is your 0 point energy, like for this case, and that is going to be 0, right? Because your EJ is, let me write it here, 1, B into J into J plus 1. So, when J equals to 0, your energy becomes 0. But can you tell me that when your energy is 0, that means your your momentum is also 0, right? So according to the Heisenberg uncertainty principle, if your momentum is 0, that means you can actually, you are pinpointing or you are measuring your you are saying that your momentum is 0. That means uncertainty in momentum is also 0, right? That means you can able to determine the momentum, that is 0. So if the uncertainty in momentum is 0, then your uncertainty in position would be, what do you think?
In-
Infinity.
Infinite.
So how do you means I will say, how will you means
How do you
justify?
locate your particle? You want to say.
Yes,
How
yes.
do you locate your particle? You want to say.
Yes, yes, because then it is infinity. I am not saying the how will you locate your particle, but how can you justify this, that your position, finding the position or the uncertainty in position is infinity, but when momentum is 0 for a rotational case, how will you justify?
Theta and phi can be any values. Can take any values. Means 0 to 2 pi and 0 to pi. Theta and
Yes,
phi.
it could be anything between that. Any possible I would say combination. So that's why it is the position, the uncertainty position can be infinity. Very good. So now we are discussing the energy of this zeroth level, or J equals to 0 is 0. Now energy of the one level would be 1 into 2, 2B, right? Then what about energy of the third level, that is J equals to 2, that is going to be 6B, and energy of the fourth level would be 12B, like that, right? And now see the interesting thing, the gap. So what you measure, what do we actually measure? We measure the transitions, right? So in spectrophotometers, what we are going to actually record is the spectrum, rotational spectrum. We record the rotational spectrum, and that relates to the energy gaps, right? So, like for the so when we are going to measure this, we will see the one when we measure the transition from 0 to 1. So then we are going to measure a line. We are going to get this delta E 0 to 1. We are going to get at 2B, right? Now, when we are going to get a transition from, transition from 1 to 2, that time we are going to get the transitional energy as 4B, right? So the gap is 7, 2 to 3 is 6B. Now you see the interesting thing, the gap between this transitional lines or rotational lines, what you are going to measure in your spectrophotometer, that is going to be always in a gap of 2b. Here also 2b. For this transition also you are going to get 2b, the gap between this. So like if you see the fourth rotational energy, then it is uh, 20b, right? The gap is 3 to 4. The gap is 8b. See, the gap between the rotational spectrum what you are going to get is 2b. So now so I told you in spectrometer what we are going to record is the rotational spectrum. So what we are going to record is actually something like this. Is if this is the intensity, the y-axis, and this is the energy, I would say, or scale is energy or wave number. Can you tell me if energy increases this side, which side the wavelength should, what should be the side of wavelength to increase, something like that? Wavelength,
Different in the
right,
opposite direction.
right, right. Actually, in spectroscopy, we generally write lambda or wavelength as a x-axis. So it could often cause a cause a con- cause of confusion to you. But for here, I would like to clear it. Anyway, so what you are going to see your rotational spectra. Suppose this is coming at 2b, 4b, as I told you. These are the rotational energies, right? 2b, 4b, 6b, 8b, something like that. So, but you will always see that they are separated by 2b. And due to that, so you can practically measure your rotational spectra. So, from the experimental value, you are going to get the 2b, right? Now, you know what your b is for. B is, as we already discussed, it is 8 pi square c, then your I, moment of inertia, and moment of inertia is your reduced mass into your the radius of the gyration, you can say, that square of that, or the bond length, right, which is actually the bond length. Now you can see from this, you know the value of h, you know pi, you know c. When you are aware of the molecule you are working with, suppose carbon monoxide or hydrochloric acid, right? When you know these molecules, then you know the reduced mass also. So from there, which is unknown, is that is your bond length. So for a diatomic molecule, which is diatomic, I would say heteroatomic, right? For that molecule of simplest case like that, we can get the bond length, right? So that's how, for using microwave spectroscopy, one of the important tool is important use of that microwave spectroscopy is that we can get the bond length. Now professor has also discussed another practical example of the uses of the microwave spectroscopy in our daily life, right? In microwave, what we call actually a microwave, right? Where we use a microwave radiation to excite or to rotate the water molecule. So what is happening? Suppose we have a samosa, right? So we keep it inside the microwave and then let it be there for 30 seconds or something like that. And then when we have it, when earlier it was cool, but now after uh, keeping it in the microwave for 30 seconds or 1 minute, we'll see it is hot. But what is interesting is that you will see the, for a specific thing, the crust of the samosa is not that hot, but inside the potato part or the smashed vegetable part, that is actually being very hot, right? That is because most of the water content is there inside there. Your that crust doesn't contain that much water. So actually, what is this microwave actually doing? It is actually heating up your water molecules inside the your food, and then it is trying to when it is trying to come to the ground state, you can say, or cool down, then it is actually radiating heat from the excited state, and that is coming as a heat energy and heating your food, and that's why you are getting your hot samosa or whatever hot food you want to have it in the from the microwave. So I hope this part was already clear. What else we can discuss here? Actually, um, maybe we can directly go to solve some numerical problems, or what else was there? Let me remember. So we have discussed the energy part. We have discussed the selection rule. We have discussed the usage. And do you have any specific query before we go to the numerical problems from the class, from the
This
student?
deviation from rigid rotor, can you please explain, sir?
Yes. So see, here actually we are taking an approximation that the bond we are using, suppose the atomic molecule, diatomic molecule, we are actually treating it as, so that is the bond is rigid. So your so that there is no change in the bond distance. Okay, so that is your rigid rotor. Now, is it actually means what I should say? Does it really happen in the physical world that you are rotating one molecule and your bond length is not changing? Actually, your bond length will change, right? So that is the case where your non-rigid rotor is not an ideal case, I should say. So what will happen that your energy that time your what is your energy for a non-red oh, I have not written one thing. I have given you these values, but the expression behind this value I hope you already know. That is your 2b into j plus 1, right? This is for a rigid rotor. Now when it is becoming a non-rigid rotor, then you will see, please correct me if I am not writing it correct. It is something like one centrifugal distortion coefficient will come along with j plus 1 square of this. Am I writing it correctly? I do not have that note with me right now. So it is what is it is going to actually your when it is a non-rigid rotor, that time your this bond distance. So I would say, see, when your suppose in your ground state, your you have a certain uh, radius. So your rotational constant is, so you have some rotational constant. Now suppose in your excited state you have a different radius, right? Or bond length. I should say bond length. So what do you expect? Your rotational constant would change, right? So that is one of the impact. Your rotational constant is going to change, and you will see that, see, this is your delta Ej, right, when it is a rigid rotor, and that time uh, for j equals to 0 your energy comes like this. Now when you have a additional term like d into j plus 1 square of that, so that time what you will see that your rotational lines will be a little I would say this will come down. You can refer to Banuel's book for this discussion. So what you will see that this actually comes down. I can use another color. So what earlier was this, and now your rotational spectrum, you will see some changes are there. Okay. Earlier what was coming at 2b, now it would be at 2b. It would be something like means suppose uh, your this transitional energy is going to change. That is obvious from your this expression, right? Energy expression. So for a non-rigid rotor, you are going to experience this. So actually, we have a numerical problem. Maybe not one, but a couple of numerical problems I have collected, which we are going to discuss today. Maybe not directly with a non-rigid rotor, but it has something to do with ground state and excited state bond length. So we'll discuss this after this. After this one's in upcoming numerical questions. So can I go to the solving of the numerical questions?
Yes, sir.
Okay. So the first question is this. So actually, this question what I am taking mostly are from the Atkins book, Peter Atkins and Julia De Paula, 8th edition, physical chemistry, Atkins physical chemistry, and also I'm going to take some numerical from the Banwell's book. Okay. Now I will not solve this question. This is very easy, as we have discussed till now. That which of the following molecules may have a pure rotational microwave spectra? The first condition was that it should have some dipole moment. So obviously, here let me use this. Hydrogen won't be having any, right? HCl will have a pure dipole moment. Does methane have a dipole moment or not? What do you think?
No.
No. What do you think about the CH3Cl?
It has type moment.
Right. So it would show rotational activity. What about methylene dichloride, or we generally tell is a DCM, dichloromethane, right? So what do you think about this? That will it have the rotational activity? It is actually DCM is a little moderate polar solvent, right? So non-polar solvents are like cyclohexane. Those are the molecules are non-polar, right? So CH2Cl2 is still some polar. What you have to do for this kind of molecule, you try to draw the Lewis structure or the norm. You try to draw the structure and then see the scale of electronegativity that where your dipole, the total dipole moment should, if it is there or not, right? And then you can judge. Like for H2O, what do you think? Is it microwave active? Actually, it is. We are discussing for a long time, right? It is a polar molecule, and I just given you the example of microwave that we are heating water molecules, right? So actually, it is polar molecule. H2O2, hydrogen peroxide. It is polar or not? It's actually polar, so it is going to be rotational active. NH3. So this is something pyramidal kind of structure is there, right? So pyramidal structure with a lone pair. So it is actually polar. So it is going to have rotational activity. What about the N2O? The structure of N2O is something like uh, this. Uh, I'm not sure if it is linear or some kind of strain geometry is there. I'm not going into that. But if the structure is something like this, even if it is non-linear, even if it is linear, you know that this is going to be have some dipole moment, right? Permanent dipole moment. So it is going to be here uh, actually going to have some rotational activity. So maybe we can go to the next set of questions. And these are very easy, but what I would like is that for so see so I have two sets of question. One set I will solve, and the other set is something like a homework or assignment. You try to solve yourself. These are very easy. Okay, so the first question is calculate the frequency of the J 3 to 4 transition. So see, this is another type of convention. So in spectroscopy, we have to follow some of the conventions, how to write the states or how to write it like that. So for this, see here it is written that for a transition, it is not written 3 to 4. Sorry, means 3 is not written at the first and 4 is not here. So it is something like J 3 to 4 transition in pure rotational spectrum of 14N and 16O. So the equilibrium bond length is 115 picometer. So we need to actually basically we need to get the rotational energy in centimeter inverse scale, or the you if you like to record the frequency, that frequency how will, so actually this is nothing but your wave number, what I was trying to say. Now you know the Bohr correspondence theory, right? Where energy is h nu, or you can either, so what I try to remember it like that. So you will see your frequency is actually your speed of light multiplied by your wave number, right? So if you have this energy, rotational energy, then you can calculate the frequency. So tell me that for a J 3 to 4 transition, what is the uh, energy gap between, or what is the transitional energy that is associated with it? So this is nothing but your 2b J plus 1. So J is your initial state. So it is going to be 2b 3 plus 1, ultimately 6b, right? Oh, no, not 6b, but 8b, right? This is going to be 8b. Now you see, you don't know the value of rotational constant for this molecule, but you know the expression, right? Your B is your Planck constant divided by 8 pi square C, and then your moment of inertia, in other words, your reduced mass into your bond length square. So your bond length is given, that is 150 picometer. Uh, 1 picometer is to how many how much meter? How many meters?
minus 12.
Minus 12 into the power minus 12. So by doing this, so these are actually very easy solve. These are very easy numericals. But with this, we are trying to do, we as a physical chemist, what we are trying, our goal is to be, we have to be correct with the units, right? So and we have to be correct, as we have to be correct with the unit, we have to be dimensionally correct. So these are the things we have to make sure during solving one numerical problem, and that is the main problem where actually we make mistakes, and there we lose our marks. We all know what rotational constant expression is, but somewhere or the other while solving this problem we mess up with the units or the dimension, and that's how we get a different balance. So obviously, you know the value of Planck constant 6.626 into 10 to the power minus 34 joule second, right? And what else we can write joule second as? Joule is Newton meter into second. So you don't have to remember joule is what? Energy. So or the, so it is Newton into meter, right? Newton is your force, and you are doing some displacement on some object, so your force into displacement is your work done, right? So joule is Newton meter into second. Again, Newton is your force according to the Newton's second law. Newton, the your force is mass into acceleration. So mass is kg, acceleration is meter second to the power minus 2, then your meter and second is there, so ultimately you can write kg meter square second inverse. You got it? How do I get the unit from joule second? You
Yes,
don't
yes,
have
sir.
to, you don't have to mug up. You just know that what joule is, right? You work done, force into displacement. Then what is the force? Force is your uh, mass into acceleration. So that's how you will do it. Very easy. 3.14 square of that. Then speed of light. So generally we want to measure our rotational constant in centimeter inverse unit, right? So instead of writing 3 into 10 to the power 8 meters per second, let me write 3 into 10 to the power centimeter second inverse. And then we have our uh, reduced mass. What is the reduced mass for this 14N16 oxygen? It is going to be mass of this 14 into 16 plus 14 plus 16, and this is atomic mass unit square divided by atomic mass unit. So it's something like 192, 14, 6, 72, 192 divided by 30, right? AMU. Can you tell me how can we convert AMU to, uh, how can we convert AMU to kilogram?
9.11 into 10 to the power minus 31 kg.
Oh, no, that though you have already given me the answer. Means I want to
Okay,
know
okay.
that what one AME is equals to one mass, one atomic mass unit equals to how much kg?
Uh, that is 9.11 into 10 to the power minus 31 kg.
That is mass of one electron.
This mass of the proton will be the equivalent.
Mm-hmm.
Actually,
Means
you
one
can,
1.6 into 10 to the minus 27 will be the answer, I
Mm-hmm.
think.
yes, that's how you can do it actually. But it is 1.66 into 10 to the power minus 27 kilograms. One AME is equal to this much kilogram. And now let me use my mobile phone. I do not have a scientific calculator at this moment. And the mass is going to be 192 divided by 30 into 1.66. That is 10.624 into 10 to the power minus 27 kilograms. And you put it here 10.624 into 10 to the power minus 27 kilograms by 115 square and 10 to the power minus 24, because 12, minus 12 and square of that is that, and meter square. So see, what I am trying to do is that now you check all the units. Huh? As I told you, we have to be very careful about the units. We have a kg here. We have a kg in the numerator. Let's cut it. Meter square gone. Centimeter second inverse. Second inverse is there. Second inverse is also gone. So now we are only left with the centimeter. So centimeter, when it will go to the numerator, it will become centimeter inverse. So our B is, I will just write it all the terms once. 6.624, 10 to the power minus 34. What else do we have? From here we have minus 10. Then when we take minus 27, it will become plus 27. Then we have plus 24, right? And at the numerator, and also the unit is centimeter inverse now. Then 8 into 3.14 square into 3 into 10.624 into 115 square. So when you do the actually the math, you are going to lead with, can you also calculate with me so that we all stay in the same page? And please let me know if I'm doing any mistakes during the calculation. Am I making any mistake? 3 into, oh, I have made a mistake at the beginning. So that is actually your One not it would be 192. It is 224. That's what I told you. Correct me if I'm doing it wrong. Something like 7.47. And if we put that here, so I'll do it again. 8 divided, sorry, 6.626 divided by 8 divided by 3.14 square divided by 3 divided by 7.47 divided by 115 square. And above is oh, I forgot 1.66 here. See, on the fast numerical, I am doing so many mistakes. Actually, you are going to get with something like 1.7075 centimeter inverse, something like that. Please let me know if you are getting that. So we have the value for the rotational constant. Okay. Now, if we have the value of the rotational constant, we can get this, your delta Ej epsilon j, that is your 8 into 1.7075 centimeter inverse, right? And that is going to give you an answer in a centimeter inverse. Now, suppose here the question, in the question you see the calculate the frequency. Now you know frequency is, as I told you, now you need to multiply your wave number with your speed of light to get the frequency. So if you do that, you are going to get 1.7075 into 3 into 10 to the power 10 centimeter inverse multiplied by centimeter second inverse. The centimeter inverse will cut, and you are going to get the answer in terms of the second inverse unit, which is your uh, so which is your 8 into 101.7075 into 3, something like 4.09 into 10 to the power. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 4.1 into 10 to the power 11 second inverse, something like that. So something like that you are going to get. Can you tell me if you are getting something in like 10 to the power 9 hertz? What is that? Simplest unit, can you tell me? We are getting something like 8.1 into 10 to the power 9 second inverse. Actually, I am asking this because in
Gigahertz.
gigahertz, exactly. So actually, I have a question later which will have will require. Anyway, so as you can see, this is very easy. But as you saw, that I myself was getting confused with the units, and that was not intentional. I was doing it because I was doing the mistake. It was not an intentional mistake. So So you also have to be very careful while solving these problems. So as you can see, you can get this kind of problem done, and then you will also be able to solve the next problem. So the problem is same. 2 to 3 transition, bond length is given, and the molecule is given. So or the I should say yes, the molecule is given with their approximate atomic masses. So you need to get the total mass. You get, sorry, the reduced mass. You get the rotational constant, get the transitional energy, and then the frequency. Okay, so this is one kind of numerical one can expect from this kind of molecule. Let me go to the second kind of numerical, where the same, the transition is given, the molecule is given, and now your transition energy is given. So if the transition energy is given, see, you know, if and what they want to asking that what is the moment of inertia of the molecule and what is the bond length. So can any one of you volunteer to solve this question? You can just tell me, and I will write whatever you are saying here. So wave number is given. Sorry, the transitional rotational transition. Which transition is taking place? 2 to 3. Then your molecule is given. Means you can calculate the reduced mass, and then your transitional energy is given. So let us. Can any one of you volunteer, and I will write. That way it would be much more interactive.
Yes, this epsilon, it is in the in terms of epsilon j in unit, so it can be simply simplified as 2b into j plus 1. This here, 2b into 3, that is 6b.
Okay.
It is
So
equal to
delta
6b.
Ej is, as you are saying, 2b into j plus 1, and that is j is 2. So it is 6b, right?
Yes,
So this
yes.
is 6b. So your b is how much?
8 by 8 pi. We
8
can
by,
count the
or it is 63.56 divided by 6, right? So 10.59, right?
yes,
So now you have you know the expression.
yes.
What is the expression? Can you tell me?
That is h by 8 pi square c mu r naught square.
Okay, very good. Now we know, and let us calculate mu then. Mu is uh, 1H or 1H and 35 chlorine. So it is something like 1 into 35 divided by 36 AMU. And then if I want to have it in kilograms, 1.66 into 10 to the power minus 27 kilograms, right? So 626 into, okay, I will not do this now because the first question is that they have asked me what is the moment of inertia. So I'll just write I. So your I will become your Planck constant, kg meter square second inverse, right? That's what we just arrived in the previous case. Then 8 into 3.14 square. C, I hope you understand, taking 3 into 10 to the power 10 centimeter second inverse is useful. And now instead of, I have taken I to this side, so B has come this side. So B, we already got it, 10.59 centimeter inverse. So centimeter inverse, centimeter gone, second inverse gone. What is left? Kg meter square, and that is the unit of moment of inertia, right? So let me calculate this. 6.626 into 10 to the power minus 34 divided by 8 divided by 3.14 square divided by 3 divided by 10 to the power 10 divided by 10.59. It is coming something like 2.64 into 10 to the power minus 47 kg meter square. Okay, this is the moment of inertia. Now, the thing we are just doing here, that your I is mu r square. So your r is actually I by mu root over of that. I we know 2.64 into 10 to the power minus 47 kg meter square, and your mu is 35 by 36 into 1.66 into 10 to the power minus 27 kilograms, right? To the power half. Your kg and kg gone, meter square is there. But if I want to take it outside the bracket, then it would be meter, right? Because it is the square root is there. Now let me do this. Divided by 35 multiplied by 36 divided by 1.66. It is coming something around 1.27 into 10 to the power minus 10 meter. So actually, if I write it like that, 127 into 10 to the power minus 12 meter, this is actually 127 picometer. So you can always play with the unit depending on what unit they want. If it is in angstrom, then you can say the bond length is 1.27 angstrom. If they want in nanometer, it is how much? 10 to the power minus 9. So it would be something like 0.127 nanometer, right? So, and as we are solving the problem in the earlier question, it was given in bond length was given in picometer. That's why I tried to give you the answer in picometer. So are you confident that are you able to you will be able to solve the next question by yourself, 13.6b, as a homework?
Yes, sir.
Okay. Now let us go to the next set of question. But the next set of question, I guess, almost similar. Obviously, it has to be similar. It is dealing with the same expression, right? But what I tried to do is I tried to gather as many kind of question that is there, so that it would be a wholesome experience. Anyway, so the question says that given the spacing of line in the microwave spectra, your 27 aluminium, 1 hydrogen. Okay, so that means it is proton and 27 aluminium. I'm not sure if this kind of molecule exists or not, or they are just making up. I'm not sure. Maybe it is there. And do you so did you heard about did you hear about this molecule earlier, or you are seeing also seeing for the first time this aluminium H hydride? What should I say? Aluminium hydride. This kind of molecule, I guess. Have you heard of this kind of molecule?
No.
No, right? I also don't. Anyway, so for the mathematics sake, we have to do it. Uh, 27 aluminium proton is constant. So obviously the spacing between the lines, what do you know about the spacing of the microwave spectrum?
That is 2B.
2b. So again, 2b is 12.604 is given. So we can get B, right? 6.302. And the rest of the thing follows as we have done earlier. What else is given? See, the extra information is given is that we need to calculate the moment of inertia and bond length like the previous case. The atomic mass unit a little bit clear. If it would not have given, we have taken 27, right? As it is given 26.9815 unit, mass unit, atomic mass unit. That's why we have to take it 26.9815. But it doesn't make a lot of change, right? What we are doing so far. So we are not going to solve this, but you got it how we are getting the B value, right, from the question. So there would be uh, different type of question, but we need to extract the value of the rotational constant, and if we can do that, and if the molecule is given, then we can get the rotational sorry, the bond length and the moment of inertia. Anyway, now the next question, same spacing is given, your molecule is given, so calculate the moment of inertia and the bond length of the molecule, and explicitly the mass is given in the atomic mass unit. I would say that you can directly write is 35 and 19. I don't see any problem that is going to happen. Okay. Because 20, 30, 34.9688, 18.9884, they are 35 and 19 respectively, right? Anyway, uh, can you, so I'm not solving the question, but look at both the question 13.7a and 13.7b. Can you see the change in the values of the rotational constant? Which rotational constant is relatively higher? What do you think?
For the lighter molecule, it is higher.
Lighter molecule. Because your rotational constant is inversely proportional to 1 by reduced mass, right?
Yes.
Right. That's what I was trying to means focus on for this question. I was not actually going to solve this, but that is one of the focus of this question. Is look at the question that the value of the rotational constant. They are huge change. See here it is something like 6.302 centimeter inverse, and in the other case it is going to be something in the decimal 0.5, 0.5, something like that. 516 or something like that it is, right? So approximately order of one means maybe 10 times, 10 time increase in the rotational constant, because the molecule is, I guess, the reduced mass is, you will see the reduced mass is 10 time uh, lighter for the aluminum hydride, the for the above molecule. Anyway, so we have gathered some knowledge from this. We can go to the next question, I guess. The next question is similar. The rotational constant is given. Calculate the ICL bond length. That is the same question as we are dealing so far, right? Now, see the value of the rotational constant again, 0.1142 centimeter inverse. And next question is 12 carbon and 16 O2. I'm not sure, it should have been 16 O2. Possibly it is. Is the case.
CO2 only, that is.
It is CO2, right? Oh, right. Then it's not carbon monoxide. So for that, then you have to, oh, and CO2 is a linear molecule, right? So you need to, but it is not a diatomic molecule. So your moment of inertia is actually is going to be a little different, right? It is not going to be mu r square. It is
Yes.
2 mu r square. It is going to be 2 mu r square. It is not going to be mu r square. I think I have a expression. You will see. Let me jump a few question. This slide, jump a few slide. In sorry for sorry for this. In this book Atkins, see there will be a table. Table 13.1 on the page 440. There you see the diatomic molecules, your moment of inertia is given. Now triatomic molecules can be symmetrical, can be asymmetrical. Suppose you have HCN, hydrogen cyanide, H carbon and nitrogen. So these are three different. So that is not a symmetrical case, but the case we are right now discussing is a symmetrical triatomic molecule, right? So the second case, and there you see your moment of inertia is 2 ma r square, or ma is your actually mass of this is not again mu, this is ma. That means your I would say this is not reduced mass, this is the mass of your oxygen. Your mass of the, if it is carbon dioxide, the mass of carbon dioxide doesn't even matter here. So these are the things you can you can try. So actually this is the question I was actually referring to earlier, but we will come here shortly. So for this you need to calculate the moment of inertia differently. Two mass of your uh, oxygen into your bond length, right? Like that you have to do. You get my point? What I'm trying to say here.
Yes, yes.
So it's not as simple as what we were looking at. Anyway, now we will move on to another question, and I guess I have taken it from the manual. From the screenshot, as I can see that I have taken directly from, I've taken an image from my phone and pasted the question here. So see here the rotational constant BE, it is written BE for a carbon monoxide with these isotopes 12C and 16 oxygen, 16O, is 1.93127 centimeter inverse. First of all, in physical chemistry, when, or not even in physical chemistry, in science, when we write so many decimal points, so many numbers after a decimal points, that means we could have we have calculated this value that accurately, or else generally we would have been happy to write it as 1.9 centimeter inverse, right? So there are these good spectrophotometers that has a resolution and in that scale that we could uh, get the value like that, and we can report it 1.93127 centimeter inverse, not 1.93 or 1.9. So the spectrophotometer is that good. Okay, so that is one of the aspect of this question I would like to highlight, that the current state of the art spectrophotometers are even better than this. Okay. Now let us come back to the question. The rotational constant is given in the ground state, and rotational constant, you see the rotational constant now decreases to 1.3099 centimeter inverse in the excited triplet excited electronic state. Okay. Now see here, I guess this is not only a rotational, the I would say here the transition has taken place from a ground electronic state of a rotational state to a excited triplet electronic state. So electronic state is changed. First of all, is that, see, the electronic state has changed, and that's why the uh, your so here we are actually in the domain of non-rigid rotor steel. Are we? Um, so here what they are saying is that when you are changing the electronic state, then your bond length is changing. If you remember the potential energy diagrams we generally draw for a electronic transition, your excited state potential energy is a little shifted. So there would be multiple possibilities, right? That what is your radius or bond length in the excited state, and depending on that, in some of the cases we can draw it something like that. That this is your potential, this is your energy scale on the y-axis, and this is your reaction coordinate, or reaction coordinate can be your bond length, bond angle, anything, right? So your potential energy in the excited state is something like that, and your ground state is like that. So, so if you think like that, then your bond length has increased in the excited state, right? So it is something like that for this numerical problem, what they are trying to ask us to calculate, that the rotational constant in the ground state is given, and your excited state, your rotational constant has gone down. Now we need to calculate the bond length of this carbon monoxide both in ground state and excited electronic state. How will we proceed? Tell me.
Two different B values they have provided, so we have to calculate accordingly the R also.
Okay, so what
Uh,
is the relation
this,
between, and we just discussed, right? What is the relation between the rotational constant and the bond length?
yes, that is H over 8 pi square C mu R naught square.
R naught square. So
Yes, 1
I
over R
can say
naught
like
square.
this.
Yes, yes, 1 over R naught
So
square.
yeah. So suppose I am writing in ground state, it is rotational constant is Bg. So Bg by, suppose excited state, it is Be. Okay. So if I uh, take a ratio of that, then the other things are same, right? Your reduced mass is same, and obviously others are universal constant, right? So those will cut, and you are going to get with your bond length in square of the bond length in the excited state divided by square of the bond length in ground state. In other word, your Re by Rg is going to be Bg by B to the power half, right? Square root of that. And even simpler, it is Rg multiplied by your Bg divided by B to the power half. So we have to calculate only one of them, and then we can put it here. So maybe for the ground state, or maybe in the excited state. What should, so maybe let us go with the ground state. Bg, as you told us, that the expression is 8 pi square C mu R G square, right? Small rg. As I should follow my own convention. Okay, Rg square. Uh, what I don't know the value of Rg, but I know the value of others. So it is H divided by 8 pi square C mu Bg to the power half. Okay. So let us calculate for once. Huh? So, but for that, I need the reduced mass. 12 into 16 divided by 28 atomic mass unit. I'll just use my mobile calculator to get the values. You also try to have the answer. 6.626 into 10 to the power minus 34 joule per second. Joule per, not joule per second, joule second, right? Then we have 6.626 into 10 to the power minus 34 divided by 8 divided by pi square divided by this 12. Okay, and what is the value of mu g is bg is given, that is 1.93 127. Let me just, so I'm getting something like this, and I need to take a root of this. So I'm getting something like 1 point. So I'm getting 113 picosecond, something like that. Sorry, not picosecond, picometer. 113 picometer. 112.86 picometer to be precise. And so this is for the ground state. Now I don't want to do that much calculation. I will just put my value here, 113 picometer into Bg is given 1.93127 divided by 1.3099. It would, you will see it would come something like 137 picometer. Obvious, because your bond length has increased. That's why your rotational constant has decreased. So do you have any questions so far on these numerical problems?
No, sir.
Not yet. Good. Now we are in the final question of our discussion today, and it may take maybe 20 minutes to solve. Uh, Not because it is hard, but because I'll try to write down it in explicit manner so that it would helpful for you. So let us see the first question. First of all, uh, we need to determine the individual bond lengths HC and CN bond lengths in a triatomic asymmetric molecule where the rotational constant are given for the individual halves. Okay, so your individual rotational constants are given. So how can we do that? Your first of all, you have this. I would say if you have H C C, don't judge my chemistry, huh? I know there is a triple bond, huh? But here, for the sake of this image, I'm writing a single bond. It's not a single bond. I know there is a, in cyanide, this is a triple bond. Please don't judge, huh? Anyway, so this bond length, suppose this is R and this is R dash. Obviously, R dash, from our chemistry knowledge, your R dash is going to be smaller than R, right? What do you think? Yes or no?
Yes.
So your moment of inertia is given. That is your first atom. I'm taking Ma as mh R square plus mass of nitrogen R dash square minus mh R minus mn R dash square of that divided by the total mass. Total mass is small m. And small m is your it's not written here? Small m is, or is it written? I'm not, can't see anyway. mH plus m carbon, mass of carbon atom, mass of nitrogen. Okay, this is the total mass. Anyway, so if I take this here, if I multiply both the side by the total mass, then I'm going to get something like this expression. I m into mH r square plus m into mn r dash square, and I can take the squares, and I will get something like m square mh square r square minus mn square r dash square, and minus minus plus 2 mh mn r dash. Okay, and the m is gone. Anyway, so what we are actually trying to do is that we have two rotational constant. So one, so, so tell me, is can we directly do it that we have the rotational constant from the individual? Oh, we do not have the separate parts. Here we what we have. See here, two kind of isotopes of uh, hydrogen is given. In one case, so it's not like one is from the Hc rotational constant for the whole molecule is given, not from an individual site. Can you see this? Uh, so we
Yes,
need
sir.
to determine the bond length of the CH bond and cyanide bond, CN bond, and the overall rotational constant is given. So for that, so if it was something like that, the rotational constant from the HC and CN part was given, then it would have been very easy that you directly, whatever we are doing so far, you would have done it like that. But here you need to get the moment of inertia for the whole molecule, because your rotational constant is related to your moment of inertia. It's inversely proportional. So we need to get some expression for the bond length in terms of the available uh, parameters. So the available parameters are, we have the rotational constant, we have the reduced mass, right? We have the total mass, we have the atomic mass of the individual atoms, right? These are the things we have. What we don't have the idea of the bond lengths, individual bond length, that is r and r dash. So we would like to get that. So what is given? Given is the rotational constant of uh, two of the isomers, right? Two isomers is given. So suppose for the first case, we are going to get a moment of inertia I, right? And what do you think? The moment of inertia is same for this isotope, or it is going to different?
Different because hydrogen H2 is there, nitrogen is there.
Yes. So let us take I dash. So now what we are trying to establish is that we will try to see what is going to be the expression in terms of I and I dash. Okay. So this is one I I into M, and then what we are doing is that let us take common MH R square. Let us take this as common. What we have, we can get M from here, and look at this minus mh square r square. So from here we can get m minus mh. Like if we do the similar treatment to the next, we can get something like m minus mn, right? And the last portion is as it is. So the agenda is clear, right? We want some expression of the bond length in terms of the available parameters. So that's why we started from the inertia. Inertia is related to the bond length, and we will see if we are able to separate those out. Okay. Now, see the first part, mh r square. As I told you, m is the total mass, and mass of the hydrogen is being, it's not there. So it is something like mass of carbon atom plus mass of nitrogen, right? Similarly, for the next, it is mass of carbon plus mass of hydrogen. And same here, 2mh to mn r r dash. So I will just do a step jump here. Huh? So this is this. Up to this part, there is no doubt. Now
This
let
two,
me,
sir, I
yes.
have a doubt. This two
Ye-
mh square into two, whether there will be two or only two is there. The
Oh,
whole,
sorry. So you're correct. You're correct. So there is no square. It should be like this. Thank you very much for the correction. Is it correct right now?
yes,
Okay. So let what I'm trying to is I will take the image to the left hand side. So if I do that, let me divide it. Let me say that I am dividing both the side by image. So I am going to get something like this expression. This expression for here, maybe I. So for the second expression, I am going to divide it like that, and this is where I am going to like get like something like this. And when I'm doing this, I'm dividing the second expression by mh. So actually, what I'm getting is that mc by mh plus 1. Are we still on the same page? I know this would be a little arbitrary at this point of time that what we are actually trying to do, but mathematically, are we in the same page? What do you think? Are we the same page or
yes,
not?
yes, yes, yes.
Okay, okay, okay. Now, if we do the same thing for the second isotope, like where it is I dash, look at this expression once again. Maybe I will write it again on the next page. Huh? So for what we got, I into m divided by mh is something like we got, let me check once, r square mass of carbon plus mass of nitrogen plus mass of, sorry, mass of nitrogen into r dash square divided by mass of carbon divided by mass of hydrogen plus 1 plus 2 mn r r dash, right? Now similarly we can write, suppose it is I dash, the total, and multiply by m dash, because the total mass will also change, right? And where the change happened, mass of hydrogen, so let me change it m dash h. Okay, so this expression is still left hand side is okay. Your new,
Yes.
it is the new moment of inertia, new total mass, and new this. But here one approximation we are dealing with, still one approximation, the non-rigid rotor, right? So there is no change in the bond length. So the bond length is will still remain the same. So the first expression is unchanged. What happened to the second expression, second term? It is mc by mh dash. Wherever we will see the total mass and mh, we will change it. So it's fine. So maybe let us write this as equation 1 and this as equation 2. So if we use equation 2 minus equation 1, then what we will get? We will get I dash m dash mh dash minus I m mh, right? So see the first and the third, this term are same for these two equation, right? So they will cancel each other. So what we are going to left with, as we are doing 2 minus 1. So first this term is there, right? Minus mn r dash square. Is it okay so far? Now
Yes.
look at the beauty of the equation. We have got rid of the r. We only have r dash. And let us go a little further also. If we try to simplify the left hand side, then we can do it something like that, m h. So we have I into I dash m dash into mh minus I m mh dash, and in this side we have these mn r dash square. These are going to get cancelled. Um, Maybe I will not do the step jump. I will let me take common mc by mh dash plus 1 minus mc by mh minus 1, right? So 1 will get cancelled. I'll just do a step jump here, right? So mc minus, so I can take mc outside, right? So I'll do that. Mass of carbon outside 1 divided by this. Now we can do the same thing what we have done earlier, right? That it would be something like mh minus mh dash divided by mh dash mh. So you can see we can cut the numerator from both the sides. So maybe on the next step we can do that. That I dash m dash mh minus I m mh dash is, sorry, then it is mass of uh, nitrogen, then square of this, then MC. Acha, let me do it like that, that I will write it in terms of R dash. So if R dash is this side, I have Mn MC multiplied by MH minus M dash H. Okay. And if I take a square root of this side, then I am getting R dash. So if it is clear to you that how we got the expression for the bond length of the cyanide part, right? Is this clear so far? And
Yes.
what are the information do we have? Let us go back to the question. We have the rotational constant for each of the isotope, right? So we have, so if we have the rotational constant B, the value we have, what is the value we have? Let me write it for maybe the first one. Maybe I'll write it B and B dash. Okay. B is 44.316. 44.316 in terms of gigahertz. Okay. So into 10 to the power 9 second inverse actually. So this is actually the frequency is given, not in the wave number. So if I have to get the wave number, then I have to divide it by uh,
C.
C. So that is your 3 into 10 to the power 10 centimeter second inverse. So second inverse gone, and you are left with, let me use the calculator, 44.316 divided by 3. That is 14. And then you have 1 by 10, so 1.477 2 centimeter inverse. Similarly, your B dash is 36.208 gigahertz, 10 to the power 9 second inverse. And that is actually your 36.208 divided by 3 by 1.207 centimeter inverse. Okay. So why your rotational constant has decreased? Because your mass has increased, because it is from uh, what do I say? It from a proton, it has become deuterium, right? So your rotational constant has decreased. Now you know the B. Now see, you know the individual atomic units, right? M, M dash. You know the total mass. So suppose what is M dash? M dash is, or maybe let us start with M. So for M it is 1 plus oxygen is a carbon is 12 and it is oxygen is 16. So how much? 229 AMU, right? 1, 12, oh, 14 nitrogen. What I am writing? It's not, it's not sorry, nitrogen. So it would be 27. And M dash would be 28, right? Because it will become deuterium. So you have B, B dash, but we are not. So here we are discussing about the I dash. So actually we from B we need to get I, and I is H 8 pi square uh, C I, right? Not C, B. And your I dash would be H 8 pi square C B dash. So you will get the values of I and I dash from here, right? From B and B dash. So maybe let us calculate, or we can do it uh, on the next step maybe. Let us write it. That your R dash, what is the expression we got? I dash MH, I dash M dash MH minus M dash H, sorry, I into M dash H divided by Mn MC MH minus M dash H is equal to, so that's what uh, is, and a root of this, right? So let us put the values, uh, or maybe in terms of expression, I dash is H over 8 pi square C, right? Uh, into your B dash, your M dash is 28 AMU, multiply by your mass of hydrogen is what? 1 AMU, minus your H by 8 pi square C B into AM is how much? 27 AMU into M dash H is 2 AMU, right? Deuterium
Yes.
divided by half and whole divided by Mn is your nitrogen, that is 14 AMU, into Mc is carbon 12 AMU, Mh minus M dash H is actually going to be minus 1 AMU, right? Because MH is 1 AMU and this is 2 AMU. So it is
Yes.
going to be 1 minus 2. So we can cut 2 AMUs from here. And as we have a minus 1 here, we can interchange the side. So first it would be 54, 27 into 2. I have cut it 2 AMUs, right? 54. And let me take, let me 54 divided by B minus 28 divided by B dash, and we can take H 8 pi square C as common, and also we are dividing it by 14 into 12, and 1 AMU still left. Okay. So B, what is the value of B we got? 1.4772. So 50, I will directly write 1 by, so 54 divided by 1.4772, right? And that is coming as 36.56, minus we are getting 28 divided by 1.207, that is coming as 23.56. 6.2 actually. Let me write it. 198 is 2. I'm trying to is the thing 6.626 into 10 to the power minus 34 a kg meter square second inverse divided by 8 pi square into 3 into 10 to the power 10, and the unit here 54 by B. So the unit is centimeter, right? Your centimeter inverse in there in the denominator. So unit coming from here is centimeter. Light, speed of light 3 into 10 to the power 10 centimeter second inverse multiply by this 14 into 12, and that is in AMU. So maybe 1.66 into 10 to the power minus 27 kilograms, and then uh, root of this. So it would something like 36.56 minus 23.2. First of all, let me cut the units where it is applicable. Centimeter, centimeter gone. Second inverse gone. Kg, kg gone. So we know we are going to get something in terms of meter square. Not meter square, but when we take it outside the root, we'll get something in terms of meter. So we are dimensionally correct. That one assurance we have so far. 6.626 into 10 to the power minus 34 divided by 8 divided by 3.14 square divided by 3 divided by 10 to the power 10 divided by 14 divided by 12 divided by 1.66. So I'm getting something as 1.158 into 10 to the power minus 10 meter. And again, this is something like 115.8 picometer, right? So this is your R dash. So this is your bond length between carbon and nitrogen as we have shown so far. So R dash was the bond length between R and R dash. So we can put the value of R dash in any one of these equation 1 or 2, and we can get the value of R. Let us see. For once and for all, I know the time is almost 9, but for the sake of it, let us see that if R dash is coming to be smaller than R or not. I also don't know. I don't know the values. Maybe that's interesting, right? Let us calculate from the equation 1. So equation 1 is your, maybe I'll go back to usual color, your I am I cross M is equal to your AMH. One of the middle equation I'm taking. Maybe I am by M is MH is R square mass of carbon plus mass of nitrogen plus mass of nitrogen R dash square, and that is given, right, 115.8 5.8 picometer square. So maybe I'll write minus 12 is meter square, right? Mn 115. Yeah, I hope this is correct. Square of this also divided by, actually not the definition. What we have is mass of carbon plus mass of hydrogen plus 1. I hope you are following what I'm doing. Plus 2 into Mn R into R dash. R dash is 1.5.8 into 10 to the power minus 12 meter. So we got the value of this I also, no? So no, we are doing it step by step. So maybe once for and all, we can see what is I. I is H 8 pi square C B, right? What is the value? I will directly calculate, huh? 6.626 into 10 to the power minus 34 divided by H divided by 3.14 divided by 3.14 divided by C is 3 into 10 to the power 10 centimeter, right? And your B is B was given, right? 1.4772. 1.4772 centimeter inverse, and that would lead to 1.89 5 into 10 to the power minus 46, something like kg meter square will come as a unit. Huh? I hope you believe me on this case. 895 into 10 to the power, and I also better calculated it correctly. Mass of total mass was 27, right? For the first isotope. So AMU divided by mass of the proton is also going to be 1 AMU. So I am not interested about this because AMU is gone. And what else is there? R square we don't know. We know the value of MC and Mn, that is 12 into 12 plus 14, that is 26 AMU, plus Mn, we know Mn is 14 AMU multiplied by this. I will just keep it like that. Maybe I will write picometer square only. And we have another expression here, MC by MH, that is again MC by MH is 12 by 1 plus 1, that is 13 AMU, 13, not AMU, right? AMU is cut. Then 2 into Mn is again 14 AMU. R we don't know, and we have 115.8 picometers. We need to get it clear. There is some cluttered. 27 into this would give us 5.118 into 10 to the power minus 45 kg meter square. On this side we have r square into 26 into 1.66 into 10 to the power minus 27 would give us 4.316 into 10 to the power minus 26 kg plus here it will give us 14 into 3, 13 actually, sorry, into 115.8, 115.8 from this side we are getting something like for the second part 4.051 into 10 to the power minus 45 kg meter square. Okay, and from this part we'll get something like the third term 28 into 1.66 into 10 to the power minus 27 into 115.8 into 10 to the power minus 12 would lead to 28 into 1.67 kilograms, 5.382 into 10 to the minus 36 kg meter, but we also have R with us. Okay, so let us see what are the things we can clear. So kg meter square, and the thing is also in the same order, so we can uh, get the second term to the left hand side. So you do a difference between 5.118 minus 4.051, and it would be 1.067 into kg meter square. And see, all the places kg is there, so let us not write it kg into 10 to the power minus 45 meter square. This is going to be 4.316 into 10 to the power minus 26 r square plus 5.382 into 10 to the power minus 36 meter into r. So this is something like a quadratic equation in terms of r, right? So we can use Sridhar Acharya's uh, equation to solve, right? I forgot it. What is like? Do you remember? Is anyone there?
Yes, sir.
Okay. Do you remember that the value of this value x in terms of the Siddharacharya's formulas that we take minus something
My
plus minus? Yes. I'll write. Can you say?
that is, I think, minus p plus minus root over of b square minus 4ac by 2a.
Minus b plus
Plus or minus. I
uh,
think I am not sure about this.
I am not also here. But can you still say it?
Yes, this minus b plus minus of root over of b square minus 4ac, b square minus 4ac, that is square root of under root of square root. Yes.
Hmm. It is something like that.
Yes.
So I think we can use this. Uh, Let us see what will happen. Most we will make some mistake, but we have done the main mathematics part. We have done. We are now doing some fun part. Okay. So let us see. So in this equation, you can see this is if I take this thing into this side, and then this equation will become zero. So your R is minus B. Minus B is this. So minus 5.382 into 10 to the power minus 36. Okay, meter plus minus B square. Square of this. Bapre. 382 into 10 to the power minus 36 square minus 4 AC. 4 into A is 4.0. 4 into 4.316 into 10 to the power minus 26, and then minus this, so it will become plus into 1.067 into 10 to the power minus 45. Oh my God, what have I done? Divided by 2a. 2 into a is 4.316 into 10 to the power minus 26. Will I'm not sure if we will be able to solve this. Is out of my hand, I guess. 5.382 into
The
10
equation
to
is
the
right, sir, but the order is very difficult to handle.
order is very difficult. Square of this plus 4 into 4 into 4.316 into 10 to the power minus 26 into 1.067 into 10 to the power minus 45. So square root of that, and 4 into this part is this plus 5.382 into 10 to the power minus 36 square of that. Okay, and we'll take root of that. Very good. We are close actually. What I'm see. I will maybe I will go to the next page. R is minus 5.382 minus 5.382 into 10 to the power minus 36 plus minus, and I got the value here 1.46 into 10 to the power minus 35 divided by 2 into 4.316 into and 4.316 I should not miss the units. Here it will become meter square. 4 into 4.316, it doesn't have any unit. And it should have meter square unit. So meter will come up. So this will be in meters. And this is also in meters. 4.316 into 10 to the power minus 26. So
We have to take the positive value only.
because it cannot negative, right? Your distance cannot be negative. So no, yeah. So I will just make it a little easy. 10 to the power minus 35, right? 10 to the, if I take both as 10 to the power minus 35, then I have to do it will become 0.5382. Is it correct? Or have I done any mistake? Or it would
Yes,
be
yes,
53.
it is correct. So,
It would correct, right?
yes, yes,
And it is plus or minus 1.46 into 10 to the power minus 5. Now it is in the correct order, I guess. 4.316 into 10 to the power minus 26. 26 and 35, it will be something like 10 to the power 9 order, right? Minus 9. And we have 2 into 4.316, and we can only take the plus one. So it is something like 1.46 minus 0.5382. We are close. Moment of truth. So 1.46 minus 0.5382 divided by 2 divided by 4.316. We have 0.107 into 10 to the power minus 9 meter. So something like 107 picometer, right?
yes, yes, sir.
But I guess this is coming less, right?
Yes,
So CH distance is lesser than, I guess, C, the triple bond end. It can be, means because your C single bond N is going to be higher than C triple bond N. But so what we are here with, your CH distance is 107 picometer, and the C triple bond N distance is 115.8 picometer. So, so the thing we are worrying about, that it should be less, which may not be true, because it should be less than C single bond N, but we don't know about the CH single bond distance. Let us check in the internet what is the bond distance in HCN. See, in the by just a Google search, I got the CN bond length as 1.16 angstrom, which is 116 picometer, right?
okay.
And the CH bond length is 1.09 angstrom, which is 109
100.
picometer. So we are close.
Yes,
So
yes,
great. So great. Uh, so I am happy that I am able to solve this. Oh my God, I
yes.
didn't thought I would have done this. I'm very sorry for my
Yes, listen, sir.
experiment. I am keeping you in this meeting, but I hope you also enjoyed solving this problem.
Yes, 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 yes.
Okay, okay. We may will do this kind of problem more often, so that at least some adrenaline rush is there.
Yes,
Or else it would be very easy numerical problems, right? The earlier ones. So, okay.
yes,
So, with that, maybe if you don't have any question, we can stop our session.
yes, yes.
Uh, and I thank you very much for joining. Um, Shumon and Shomitra, both of you.
Yes.
I hope both of you will join on the next session and we'll discuss the vibrational spectroscopy problem. If you have any doubt, please write it to the discussion forum. You can even directly write it to my mail ID, arkapravachaudhary@gmail.com. My name @gmail.com. There is, so you can obviously reach out to me. And these sessions recordings are available on the YouTube, and the notes are also your drive links will be shared to you. But I will prefer you to directly join on the Google Meet so that the session could be interactive and it is much fun that way, right?
Yes.
I hope I will meet you on the next session, and thank you for joining. I hope you have
Thank you.
learned something from this session.
Thank you.
Good night. Good night, both
Good
of
night.
you.